Some of you probably have learned from physics class that we have four different types of forces in the universe. We have strong nuclear force, we have weak nuclear force, which we usually don't deal with these two types of forces. We can see it between particles in an atom, and we don't really work with them in engineering. But two other type of forces are electromagnetic forces and gravitational forces, which we usually in our ordinary life we deal with these two type of forces, right? When I'm pushing my finger, for example, to this paper, the molecules of my finger and this paper, they have there is an action and reaction between them, right? These molecules are applying forces to each other. That's electromagnetic force. But what is gravitational force? Newton tried to explain the motion of all the planets and stars after gathering all the previous works together and tried to explain all of them with one equation. He finally came up with this equation, this gravitational law. Based on this law, if you have two masses, they can be small or big, anything. Let's say we have two particles or two spheres, perfect spheres. And the mass of them are m1 and m2, and the distance between these two particles is r. Based on this law, these two particles are going to apply a gravitational force which has the same magnitude but in opposite direction. So it is kind of these particles are attracting each other with this force F. And the value of this force, the magnitude of this force, is proportional to these two masses, m1 times m2, and inversely proportional to the distance squared between them. And the ratio between them is a constant, which we show it with capital G, and it is constant of gravitation. So Newton showed if we assume each two particles in the universe, they apply force to each other, which we don't know what is the nature of it, but if you have this type of force, then we can explain all the movement of all the planets and the stars. And this force must be proportional to the mass of both of them and inversely proportional to the distance squared between these two. But he never actually found this constant. But after doing a lot of careful experiments, centuries later, people found this G, which is constant of gravitation. And the reason actually they didn't find it easily, and it took a lot of time to find it, because it's a very, very, very small number. It is 6.673 times 10 to the negative 11 meter cube divided by kilogram second square. So because this G is a very small number, if your particles have small masses, like any ordinary masses, like 1 kilogram, 10 kilogram, if you multiply 1 and 10 and multiply to this very, very small number, then the magnitude of that gravitational force is going to be very small. So this force become significant if one of the masses is really big. For example, one of the masses become Earth. So if you consider the Earth with the mass of ME, which is very big, so this is the Earth. The mass of the Earth is 5.976 times 10 to the 24 kilogram. And the radius of it, RE, is big as well. The radius of the Earth is 6,371 kilometer. So So if you consider any particle here, like for example your body, with a mass of m, the gravitational force between these two is the weight, right? The gravitational force, we call it weight, and we usually show it with W. So the Earth is applying gravitational force of W to this particle, and this particle is applying the inverse of it to the Earth. And the magnitude of this force, which we call it weight, is equal to G times mass of this particle times the mass of the Earth divided by the distance between them is squared, and the distance between them is going to be the radius of the Earth, right? If the distance of this particle is just a little bit above the Earth, like 10 meter, 100 meter, it's going to be just negligible compared to the radius of the Earth. So RE squared. And from the other side, if you remember in your physics in high school, whenever you want to calculate the weight of something, you use this equation, m times g. And g, usually you consider it 9.81. And that g comes from this equation. Actually, this g is capital G times me divided by radius of the Earth squared. So g, gravitational acceleration, we should usually use it, consider it 9.81 meter per second squared. It comes from here, g times mass of the Earth divided by radius of the Earth squared. Because the radius of the Earth is different in different locations, g is going to be slightly different in different places of the Earth, right? Yeah. But again, we use this equation. We said the distance between these two particles is the radius of the Earth, because we are assuming the altitude of the mass is negligible compared to the radius of the Earth. But if the altitude of that mass becomes significant compared to the radius of the Earth, like for example for a satellite, or maybe moon or other planets, then g is going to be different, right? And the distance between these two is not going to be the radius of the Earth. It's going to be totally different thing. So if the altitude of this mass from the surface of the Earth, if we call it h, and h is significant compared to the radius of the Earth, then the weight of this particle in that altitude is going to be g times mass of it times mass of the Earth divided by the distance between them is going to be RE plus the altitude h squared, right? And again, if I want to call show this with mg, this g is not going to be 9.81 anymore, right? Because the denominator is a totally different thing here. So to show them with different symbols, I'm going to call g close to the ground by g naught, which is that's 9.81. And in different altitude of h, if I show it with this g, then this g is going to be capital G, constant of gravitation, times mass of the Earth, divided by the radius of the Earth, plus h squared. Right? Because we have a bigger number in denominator, then g is going to be smaller than g naught, right? Or if you want to compare them together, we can divide these two equations together. So g divided by g naught, g and me, they're going to cancel out. We are going to have g divided by g naught is going to be radius of the Earth squared divided by radius of the Earth plus h squared. This is a useful equation to find constant of gravitation, to find gravitational acceleration in different altitude, for example, for a satellite or anything else.